So, dear ladies and gentlemen, good afternoon. Wow, I'm still a little bit impressed from this great presentation before. So, yeah, I like to catch in the beginning of my talk a little bit this idea. Yeah, we are a little bit in the same situation. We have a great measurement technique, a so-called impedance spectroscopy. We have since almost 2 decades the international workshop on impedance spectroscopy in our house. And yes, we have also this problematic how to get in charge, how to get in contact with industry, how to get this procedure in production processes. And yes, more than 10 years ago, yet we face it. We need embedded impedance spectroscopy, small adapted application-specific impedance spectroscopy to get out this great procedure from the lab into production processes, into small and mobile devices in an economical way. And in the next minutes, I like to catch you a little bit how far we come in this field, and the title, Real-Time Diagnostic for System Industrial Processes. For the beginning, I like to introduce our team a little bit. I represent here Mrs. Professor Kanun, my chef in our nice university, Technical University in Chemnitz. We are a great team of up to 40 researchers in a lot of different fields. We are developing sensors, sensor materials, sensor systems, but also wireless and also Internet of Things to play with the data is on our screen. Because of the capability of the procedures we are dealing with, we are in almost all technical branches: automotive, industry, environmental, medicine, and energy. I guess you will get a picture in the next minutes. Okay, first of all, I like to introduce a bit more our team. We were starting in the past with 3 different working groups. Yeah, as I still said, impedance spectroscopy. This is also the working group I am leading right now. We were starting with a team dealing with wireless sensors, wireless communication, autonomous power consumption, something like this, were topics developed in this group. And also the field of physical sensors. We try to utilize polymers for a couple of different physical principles. We were starting with strain and pressure, but in the meanwhile, we are developing also electrochemical sensors, for example. The experiences we collected here in the field of polymers, in addition of this powerful instrument, the impedance spectroscopy, this allows us to go in this branch of electrochemical sensors. And finally, our youngest working group, wearables, and these are sensors, touch it to the human body anyhow in a shoe or to monitor in medical devices like here, lungs monitoring. In this group, all of the other working groups were contributing to develop new approaches. Okay, what is the motivation? The motivation for our work, yeah, everybody is speaking about sustainability in especially manufacturing processes. This is our motivation. There are a couple of different aspects intrinsic coming from inside of the company. Yeah, the idea or the need to reduce power consumption for production process, to reduce resources or to deal in an efficient way with the available resources. For sure, for companies, cost reduction is important, increasing quality, yeah, for sure. Each company like to do the best for their own products, and at the end, less rejects. In the last years, we faced also problems in the supplier chain. Yeah, so it is the idea to increase also the number of potential suppliers for the own products, and also the aspect circular economy to reuse materials. This is also an aspect becoming more and more important from inside the companies. From outside, there are aspects like CO2 pricing. We have also this so-called Corporate Sustainable Reporting Directive, CSRD. The companies are called to monitor their own effort to reduce the CO2 footprint. Also, the consumer attitude changed in the meanwhile. Yeah, there are a lot consumers nowadays asking, yeah, what about your CO2 footprint, especially in a production process? Yeah, and at the end, this is only an example. The new European battery regulations, there occur a lot new questions in this direction to get a better view into manufacturing processes. For my talk right now, the focus will be more on the CO2 footprint, optimizing of energy and resources utilization, and the efficiency of production processes. So, first of all, that you get a better picture of what we did, I like to explain a little bit the idea impedance spectroscopy and what does it mean embedded impedance spectroscopy. And yeah, now a short lecture. I apologize a million. Impedance spectroscopy, that means I need an excitation signal. Yeah, in a standard way, a sinusoidal signal. I apply this excitation signal to a device under test. And for, in that case, I choose the device under test, the battery. The excitation signal is applied to a device under test, and I get a certain output signal. Here in the IU curve, you see the excitation signal applied in a certain working point, a state of charge from this battery, and you get a corresponding response, a reaction from your system. So, and this reaction you can calculate to one point in the Nyquist diagram. You see the real part and the imaginary part of impedance, and this is at the end one frequency measurement, and this describes almost the state of the art of impedimetric sensors. If you take a look, eddy current sensors, capacitive sensors, ultrasonic sensors, all these sensors almost working with one dedicated frequency. So, and from the point of view, fundamentals of measurements, yeah, we are teaching also in our university, our students, and still, if you use a second frequency, you increase the robustness of your measurement a lot. So, and like this we use a lot frequencies. Yeah, you see here a so-called sweep from a low frequency to a higher frequency. We apply a sweep of excitation signal to this working point, and for sure we got also a certain response depending on your behavior of your system. And yeah, this becomes more clear a little bit further. And here each system has a typical characteristic, and so the problematic is to design an adapted excitation signal for a dedicated system to get a characteristic curve like this for example lithium-ion battery. So, and this is at the end also our advantage, our skill in our team. Our idea is to get as good as possible understanding what happened, especially in these frequency ranges. I guess later on this aspect became more clear. If you take a look, you have here now a sweep of a sinusoidal signal. you put one frequency after another, so you have a great measurement time, yeah? So, and for fast impedance spectroscopy, for sure, there are a lot of opportunities, a lot approaches to reduce the measurement time. And here, only one example, multi-sign. You see here 2 periods of the smallest frequency, the longest period duration, and we put all the other frequencies into this time window, and we apply at the end a multi-sign signal, and at the end it is possible using signal processing to analyze each frequency point separately. Yes, the advantages, it is a non-invasive approach. We apply this for resistive, capacitive, or even inductive solutions, approaches, sensor principles, yeah. And one benefit is also another benefit, separation of effects in the specific frequency ranges. A collection of our approaches, we were able to characterize materials like metals. Therefore, we are using almost inductive sensors, eddy current sensors. We call it inductive spectroscopy. We developed an approach for cable diagnosis, yeah, well-known also batteries and fuel cells. For biomedicine, we developed approaches in this food branch, oil or milk. We apply always capacitive spectroscopy. At the end, we use capacitive sensors, applying multispectral excitation to get more information out of the system, out of the measurement in comparison to state of the art. And the idea is to get this principle, this technique into an embedded system for first stable, affordable, embedded impedance spectroscopy. Yes, but what does it mean, understanding of impedance spectra? You see here once again qualitatively this curve, this Nyquist diagram from the slide before. And this is a typical shape, qualitative, and we start here in this part in the range of millihertz. Yeah, batteries, this is an electrochemical system. The effects, the phenomena were slow. You have ionic charge transfer. That's why you need low frequencies to acetate, to analyze this range or these phenomena. Yes, we start here. This is a so-called RS point, the shift of the real part. This is not so very much important, but this is an important method in the state of art for battery diagnosis, the 1K method, yeah. But honestly spoken, without any sense. So we have here this diffusion part, as I said. This is coming from the electrochemistry field, well described in this area. We use this information to model this area. Here we describe almost electrochemical phenomena, electrochemical aspects in the battery. So you need to understand, we have this excitation signal, a low frequency. At the end, it's a polarization of the molecules from the electrolyte. So, but the electrolyte molecules are very huge. And if you increase the frequency, the heavy weight of these molecules is too much that they cannot follow anymore the polarization, the excitation. And that's why this phenomenon get out of the contribution for the measured signal. And this is this point. And from this point, another phenomenon becomes obviously. And you see here in this area, there is a semicircle present, and this describes almost the characteristic of electrode 2. In this area, there's also the so-called charge transfer reaction active. I continue. There is a small semicircle. This is electrode 1. Also, delamination phenomena can be monitored in this area. And then there is a small inductive area up to a small kilohertz range. Yeah? And this inductive part is almost important for, let me say, fast charging aspects. Yeah, if you like to design an embedded system, or no, not an embedded system, a battery management system, for such for such purposes, it is important to know the inductance of your system. Our idea is to get real measurements, to get understanding of the working phenomena in this area, and to organize a certain modeling in such fields. Generally, let me say, we can distinguish between two modes. I apologize, German language, wow. I divide a qualitative understanding. A qualitative understanding, it's at the end, it change from a certain state, yeah? If you have, for example, a good example in your production, you measure a curve, and this is your best pattern, yeah? And then, if you continue in the production, and you have any kind of a failure in your system, you have a change in this shape. And this is, in our understanding, in our talk, a qualitative mode. A quantitative mode, this is a little bit more, this needs a little bit more effort in the lab. We need a better understanding, and we need to generate a certain electrochemical, a physical model which describes this characteristic. Yeah? And if we have such a model, then it is possible to extract really physical aspects or phenomena which we are changing in the procedure or wherever. Yeah? But I guess you will understand later a bit more. This is a very much important diagram for our team. Yeah, you see here an x-axis, this is a frequency range. You see the decades, 10⁻⁶ up to 10⁻⁹. And here you see the impedance range from also 10⁻⁶ to 10⁻⁹. Yeah, this is almost a range of practical applications. Yeah, and you see here the field for batteries, for example. You have a range from 10⁻⁵ up to 10⁻�3, so you have a small kilohertz range where we acetate the battery systems, and you get at the output impedances in the range up to ohms. As you know, lithium-ion batteries, for example, they have an inner resistance of some milliohms, and we don't need to have a system with a resolution kiloohms. Does not make sense. Yeah. So, and which effects are working? We have here double layer effects in the region 10⁻�3, and we have ionic conductivity in the range of hertz. So this is only an example. I don't like to continue with each phenomenon. This is our magic diagram, and each application, we put always here into this field. Let me make it short. We have here affects, we have here our coil structures, the inductive spectroscopy in this range. Here we are using eddy current effect or the Maxwell-Wagner effect. In the range 10⁻⁷, we have almost active water molecules. If you have, for example, absorption of water in polymers, in wood, in whatever, yeah, then we need an acetation in the field of 10⁻⁷. Yeah. So here in this area, microstructures, 10⁻⁹ polarization effects. So this is something we are currently more concentrated in. Our idea is to identify polymer types, and there we need to go down into the molecular level, and there we use polarization effects from polymer molecules, and there we need to go up to gigahertz range. So here you got a clue. What does it mean to have frequency-dependent effects or phenomena? Yeah, these are very much important for us. At the end, our strength or our idea is always to make an impedance measurement and to get a certain understanding what happened. Yeah, so the idea is to get a physical or an electrochemical model. And for sure, to make the story short, no universal measurement device is able to cover this complete range. Yeah, so this is too much for one approach. So, and this is also a challenge we are faced. As I said, for us important embedded system design, and therefore you need to keep this part in your mind. Yeah, once again, impedance spectroscopy in lab, this is something you can go in a shop and you can buy devices. Not on the fair, but Keysight, you can take 60, 70 kilo euros, 70,000 euros, and you can buy impedance analyzer. But I'm sure you don't want to put this device in your production line. Yeah. A next step is a National Instruments hardware. It's possible to apply also with such components impedance spectroscopy. You can use the parts, the components. You can do it. It's possible. But at least if you need to multiply and you need the second and the third license, also this is not so really funny. That's why the solution is we need to develop embedded solutions, small circuits, cheap, robust, and fully automated. But I need to say, limited resources. Yeah, you have always limited resources. You have not the full performance. But do you need it? Do you need it? So you need to take a look into your production process or whatever. And you need to identify these points which are important. And then you can reduce your measurements to only a small frequency range or even only some frequency points, 1, 2, 3, 4, to get a sufficient information from the procedure in the embedded approach. And this is at the end a final overview from theory. What does it mean at the end? Impedance spectroscopy is a complete story. You need a dedicated, a synthesized excitation signal for your particular approach. You need to measure the signals, the voltage and the current, and this is important in phase. Yeah, you cannot measure sequentially with a multiplexer. This is not possible. It is possible, but you have problems with the phase at the end in the analysis. You need the impedance determination, and yeah, these are the parts which are almost combined in the embedded system, and the data analysis, this should be done somewhere in a cloud or wherever in an addition part upstairs. Let me say it in that way. So now I come to this, yeah, I call it philosophy, to get a better picture from your manufacturing processes. And yeah, I have here such a nice diagram. This is a sample, a draft of any kind of a production line. Yeah, you have incoming goods, sure. You have in your production, you need to deal with liquids, with inks, with glue, with process water. Anyhow, you have the field of polymers in your production process. You have the field of metal-based products in the production line. And at the end, you have an end of line. And in the end of line, you are almost all dealing with systems or products. So, and let's take a look. We have raw material, liquids, polymers, metals, and at the end, products. We are going stepwise, characterization of raw materials and incoming goods. What does it mean? Yeah, how does it work until now? You were a company, you need a certain supplier chain. You go to your company and you say, I need a product, XY, this is my specification. Can you deliver? Yes, no. If yes, everything is fine. No, then you go to the next. So you have a quite tight band of tolerances for your products, for your incoming goods. But what will come soon? You have tolerances in the supplier chain because of availability. Yeah, you know the complications in the global infrastructure. You need to go to a different supplier. So in there, cannot give these tolerances. What do? Do you stop your production or do you adjust your production processes? Yeah, you have tolerances in the supplier chain. You have also tolerances because of the idea to use natural products. If you like to use polymer, you want to substitute your polymer with, for example, natural fibers, for example, you won't have any more this stable parameters. This is sure. And also the question recycling. You get much more problems because of aged or anyhow still in use aged material. Yeah, there are a lot investigations in that field, but this will come soon. Yeah, to increase the sustainability, reduction of rejects. These are the questions. Increase of quality or to keep the quality of your products. Improved availability. This is almost the story with the supplier chain. If you are not, if you don't have the need to go only for one supplier, and at the end, all these aspects help to increase the sustainability at the input of your production. In that case, I don't place an example from our research. I want to continue here. Dispersion monitoring, capacitive spectroscopy. Yeah? If you are dealing with liquids, as you remember my diagram, we were dealing almost with capacitive spectroscopy. What can we do? We can, for sure, we can measure filling level, but we can also characterize liquids. So here we have, as you remember in the first overview, we have a team also developing soft sensors. Yeah, published in 2022. We try to organize dispersions, included nanoparticles. And here you see almost the biggest problem. You have the CNT, the copper nanotube, for example, and the copper nanotube like to stick. Yeah, like to stick. There are van der Waals forces. That's why this material like to conglomerate, as it is shown here. But this is an unwanted problem for the production of, or yeah, for whatever you want to do with this polymer. Yeah, as you see, some aspects are quite fundamental, but we do here soft sensors. You can see our startup in Hall 1. Yeah. What is our approach? Here you can see the mixing process in a epoxy dispersion. We bring epoxy in a solvent. We have a dispersion and we mix it with carbon nanotubes. For sure, if you put it in the first, it looks like this. Yeah, you have sedimentation, you have different phases, no homogeneous dispersion. And yeah, we need some time to develop for different polymer types. Yeah, always dedicated procedures, including ultrasonication, steering, and heating procedures to unbundle the CNTs. Yeah. So, and what does it mean? We have here once again the conglomerates, and by sonication time we get an unbundling of the CNTs. And the final goal is at the end a homogeneous distribution of the CNTs in the dispersion at all. So, problem in this point, if you continue with sonication, the CNT breaks. And this is once again an unwanted phenomenon if the CNTs became shortened. We want the CNTs in the best in the origin length. So, and this we are able to monitor also with impedance spectroscopy. And you can see here a corresponding model. So this is a procedure we understand in a well way. this is ready for industrialization. Okay. As I said, published in 2022, and we have here a startup in Hall 1. Another example for container monitoring, we have here a commercial proximity switch as a sensor used, yeah, a capacitive sensor with a single frequency, and we manipulate it, and we use a multi-frequency excitation signal, and we were able to distinguish between medium and a conductive film, which is occurring inside a tank if you have a certain stiffness of the medium at all. Also, such things are possible using impedance spectroscopy, in that case, capacitive impedance spectroscopy. Further possibilities, liquid quality, as I said. Yeah, let's think about the production process. You have your production line, and you have, for example, a tank with the ink or with a glue. You don't need a lot in your process, and this tank is there 1 week, 1 month. Maybe you have sedimentations, you have drying procedures, and so on. And yeah, we can support this by observing with impedance spectroscopy to make this procedure more stable. Coming to the next stage, polymers. So in the field of polymers, we almost use also capacitive spectroscopy. What does it mean? Here I choose an example in a production process of printed batteries. Yeah, as you can see, you have here a pattern printing process. You have a huge substrate where you have multiple, I call it a matrix, of pads which were printed and in a sequence. You have a first printing process. After a while, after a drying procedure, after a evaporation or a formatation, you have a second procedure. Yeah? And I am sure, still in the first step, the quality of the final product will be defined. And I am sure you have in this matrix 1 or 2 or 3 parts which are rejects from the beginning, from the first procedure. Eins, zwei. Okay, ich bin wieder da. So, there is impedance-based battery monitoring missing. Okay, so coming back to this talk, yeah, and I am sure that there are parts included which never reach a final product. So, and what is a state of art? They were processed until the end. But nowadays, it is absolutely not a problem to exclude them, yeah? That at the end only some parts of them become ready. So, and what you can see here, this is only a qualitative drawing. You see the pattern of the battery diagram. Yeah, so you can measure in the lab the spectra of an idle process result. Yeah, you get from the company an idle process result. You make the impedance measurement, and you have this in your system, and you have a model parameter set 1 for the first layer. So how does it work at the end is not yet clear. If this is included in the nozzle from the printing head, yeah, or if it is something like a mask which you put on it after the printing procedure. This is not yet clear. Yeah, it depends on the application. But what is possible? You have, after a while, a second printing procedure. you take the same application, the same sensor system, the embedded system for impedance spectroscopy, the same front end, a capacitive structure, and you select in the microcontroller only the second model set for this double layer structure. For sure, this double layer structure you characterize in the same way in the lab before. So you are able to analyze. I don't want to do that with each step, but with the key steps, the important ones. At the end, we have such a matrix. Yeah, it is published in 2024. We are able to analyze impedimetric matrix systems. I don't want to come in detail here, but we can do that. What is the idea? We have here our impedance-based measurement. We are able to measure each of this matrix element in a way that we can say, okay, this and this is okay, and the fourth in this line has any kind of a problem. Yeah? And my system maybe can adjust process parameters. Maybe here you see the yellow arc. It's maybe in the range of the tolerance band. Yeah. So here you can adjust the parameters, and this you exclude from the further production steps. Embedded systems for impedance measurement in matrix structures. Yeah, we start in this year with a project. We develop this with a company doing printed batteries in our town. Okay, what else can we do? Yeah, identification of percolation threshold by IS. Yeah, so here you see, for example, a micro image of the polymer with a CNTs, and the percolation is at the end a conductive pass through this structure. In that case, it's a P.PSS polymer substrate. So, and here you see first a diagram. The dependency of the conductivity depends of the concentration of the CNTs. And what you can see here is a characterization of the forming procedure. We have the printing, and afterwards, in the drying procedure, the forming of the structure. Follow it by impedance spectroscopy. So we can measure, okay, in front, analyze it in the lab for sure. What is the best time to continue with your process for the next step? Yeah. Further optimization criteria. We have here our sensor main structure, and we have here application, addition textile, whatever. And we try to apply directly our ink. And here you see the result if we have a slow squeeze speed and a fast squeeze speed. Yeah? The speed of the Rakel causes the quality of the homogeneity of the result at the end. Yeah? And for sure, you don't like this, you want this. Yeah. And as I said, we try to understand always the story. We try to organize corresponding models for later automation procedures. And here are some diagrams. I don't want to come in detail. You can read, if you like, published 2022. Okay, next step, polymers solvable. Metal and metal forming procedures. And in that case, we use always inductive spectroscopy. At the end, we use inductive sensors, and also with a multispectral excitation signal. Forming of diameter stress during the forming process, there are a lot of aspects. First of all, I want to start with a PhD running in our team in the detection of wire diameter deviations in hot rolling. This is a crazy technique if you see it with your own eyes. This is a harsh environment. These are great factories. You have dust, you have humidity, you have heat, and you have a rod which is rolling hundreds of meters per second. In that case, we apply also a coil, an inductive approach, working by up to 900 degrees. So here's also a cooling system included, and we are able to identify such shapes. So we were detecting simply the shape structure of this rod, and what you can see here were examples for failures causing from process parameters in the process. Yeah, if you like, you can read in a dissertation from our team. Next step, these are ongoing research investigations. You see here a cold forming procedure. You see a part, a metal part, a tool, and you see here cold forming. What does it mean? You have localized a lot of stress. You have localized a lot of heat, and you want to know what happened. And here we developed also inductive sensor approaches, contactless, in real time, very much robust in a compact size, and it's very interesting. And we use the eddy current effect. We have a coil. The coil organizes a magnetic flux, a magnetic field, which is going into a target material. And here we use also this, as I said, approach with a multispectral information. A lower frequency causes an eddy current, which is going deep in the substrate in the target material. A higher frequency is only scratching at the top, so-called skin effect. Yeah. So in this we can use in different kind of sensors. And here one example. This is a so-called MST flower. This is our flower from our team. A main coil for the agitation and sensing coils around this center. And with this structure, we are able to detect the magnetic permeability of a material and also magnetic anisotropies of the material. Yeah, as I show here. Yeah, you have in that case only the primary coil in use, but for anisotropy measurements, you use also the sensors, the coils in the surrounding of the structure. So, and what can you do? You have this structure. This is at the end a measurement without strain. And if you have in your target material a strain, then you have this deformation of this curve. These are polar coordinates, and you have this deformation of this curve. What does it mean? We have here a strain measurement, a contactless strain measurement of any kind of a metal target material. So you can measure tools in operation, you can measure whatever strain in a material. And to make the story short, we can detect changes in the permeability of the material. And all aspects which causing a change of the permeability, we can detect. And this is, for example, strain, temperature, also the grain growing. Yeah? If you make hardness, for example, you have bigger grains causing a change in the permeability. We can measure with our sensors the deepness of a hardening procedure, for example, without destroying it. And also the relief, the surface, we can observe. Yes, and one aspect from the lab, we had in the past measurements we were observing a soldering procedure, and this was such a harsh environment, our laptops dropping down, and the sensors were working properly. What is also interesting with this principle of this multiple sensing, we are able to identify unwanted or external influencing parameters. Yeah. So here, for example, you have tilting. This is always a problematic with inductive sensors. What about the positioning or the orientation of the sensors? We can detect tilting, and this is also quite interesting. We can measure anisotropies, and that is a gradient, a movement. Yeah. One example from the practice, if you take a look to the development of pouch cells, for example. Yeah. For the research, it is very much interesting to understand or to know how the current is distributed in a pouch cell. This is a very important information for them. With this sensor, we can detect where the current is flowing in a pouch cell. By the way, separation and qualification by Fourier analysis. Once again, we we are working also here with a multispectral, with a dedicated synthetic multispectral excitation. So, end of line testing. I like to use always the battery as my device under test. Here you can see such a comparison study of 4 different cells. So to explain this measurement, you see here the 9 different stages of the SOC of a battery. And in each stage, we made the impedance spectra of the cell. Yeah? So you see the typical increase of the curve by charging. Yeah? So, and what do we face, and why do I put this slide here? You see in cell 3, we had here a phenomenon. Exactly the SOC 70%, the impedance spectra run away. So, if you take a look here, 0.5 ohms, real part, easy, no point, yeah? But you need to understand the 70% SOC will really use it in practice. You know, batteries in practice will use it only in a small range, but 70% are in, yeah? So if you have this phenomenon in maybe 20 or 30%, doesn't matter, but 70% will use it. So, and that means the double real part. That means the double heat losses. So you have in your stack a source for a hotspot. So, okay, in that case we go a little bit more deep, and we found that in this cell, these were new cells from the market, the forming procedure was not yet done completely. After a while and after some cycles, this part decreased a lot. But once again, this is an example to show how impedance spectroscopy can help to improve your processes. And here at a complete system. Yeah, impedance spectroscopy in the field of batteries we did for almost all battery types, for all chemistries. Yeah, and you see here naturally also a change in the shape. You need for all the batteries, for the different types, different models. But this is at the end our homework we did always to get the understanding and the physical model of your cells. Yeah, and yeah, I have here also lead acid batteries, and I am totally convinced that this type of batteries will follow us the next decades as well, even if the European Commission don't like them, but because of this high quality factor right now in production, and also the reuse of the lead acid batteries, it is really a system we will need in the next years also for the energy turnaround which is going on. Yeah, and here we have a comparison study from our USV system in our university to get a better understanding what happened with the cells. And here we face really, you see here a string of batteries, and we face that really the corner batteries, they got more in charge with disturbances from outside, from the converters, from the rectifiers, and we face really at the corners of such a stack bigger change in the characteristics. Okay, now I am almost at the end. You see here once again such a complete line. Totally missing are our approaches in the field of bio and medicine and food and agriculture and environment. I was focusing only on the manufacturing procedure, but I guess you got a good impression, liquids, polymers and metals, how impedance can help to increase the sustainability in such processes. We need at the end embedded system in a certain frequency and impedance range, a certain front end, to get the interface between this measurement and the real world. And that's our job. The final end I like to introduce, the 17th, in the meanwhile, the 17th International Workshop on Impedance Spectroscopy, each year in the last week of September. Yeah, you can come to us in Chemnitz. and this is a nice, kind conference. We got visitors from all over the world discussing about the different facets of impedance spectroscopy. And if you don't have time in September this year, May next year, you need to come. Yeah, this is a IMTC. We are totally proud on it. Also here a certain banner. This is for our section one of the most important conferences. We are totally happy to have this in Chemnitz. And yeah, please take the QR, and I hope to see you next year, latest next year, in our hometown. We try to organize unforgettable time there, and there's also the anniversary, the 75th anniversary of the IMSOC, the Instrumentation and Measurement Society, and yes, you are welcome. Thank you.
Thank you, Thomas. Thank you for your very impressive talk. Are there questions from the auditorium?
I'm just going to stand over here because if I'm right in front of the speaker, it gives feedback. So if I understood correctly, you can use this technique in the manufacturing, but you also kind of hinted, maybe jokingly, that it could be used to detect in real time for failure in a device. Can you explain a little bit more about that?
Yeah, what does it mean real time? Yeah, so with our I have shown this little example, yeah, with the coins. Yeah, this is one of our first ready solutions. We develop it for in-process, embedded in-process solutions. We have a company in Chemnitz. They are dealing with coin count devices. Yeah, and there's also the question counterfeit detection. And state of art are camera-based optical procedures. No chance you don't identify counterfeits anymore. Yeah, the counterfeits are too much good from outside. But what is not possible for them, the inside. There is a certain nickel structure inside, and we were developing an approach. For sure, we start in our lab. We got a certain understanding, and the embedded system at the end is a microcontroller with some kilohertz sampling frequency. We are applying also a undersampling approach. We are detecting frequencies more upwards, yeah? And we have two coils, two different frequencies, and we measure more than 300 coins per minute. So it was really a fancy thing. If my colleague start a measurement, you hear it in the complete department. Yeah. So, for sure we use also KI in all of our measurements. It doesn't work anymore without. Yeah. So we made a rough, reduced measurement with a reduced infrastructure, with a reduced hardware, but by using KI we were able to classify, and we have a very high rate to detect, to identify the counterfeits. Yeah.
And the follow-up there is, did you say there's a company interested in developing this, or is it just a demonstration of the technology?
Now this solution is integrated, and it's really a nice story, and we continue with them, and at the end, this is also at the end a KI question to go for addition coin systems all over the world. Yeah.
Other questions? I have a final question. This is very interesting part for the digital product path, you know, because these are all informations which are very important for the product path for batteries and so on and so forth. Do you have connections to this?
Yes, we have connections also to people which are participating in this procedure on a European level. So, but for sure, we need to show face.
Okay. So, thanks a lot once more for this wonderful presentation. And now it's time to close the forum for today.